You know, the title is really towards technicians who decide that adjusting an oil burner by sight is acceptable. And although they may sometimes get half-decent results, there'll be those times that they won't, and those are the concerns. So that's, you know, that's what we try to address. I actually found this set of instructions on the internet on how to set up an oil burner by color. So you see here, this gentleman is already at step 4, and he's telling you what color the flame should be. And if you're not seeing the right color, and I think he's mentioning a bluish or whitish flame, you can just make small adjustments, moving the collar until the appropriate flame color is reached. I don't know if this gentleman is in our trade or in the business or even still alive. But clearly, you know, these are the kind of things that we try to avoid. When a flame, and we still say that nobody can adjust a flame correctly by sight, but if you do get it clear, it would look probably something like this, and you know, you might be able to cook your hot dogs on there. I wouldn't eat them, but it is possible to cook your hot dogs.
Angel, B100.
Yeah, B100. Again, here's a flame. If you're adjusting by sight, it's unpredictable. You're not really sure what you might get. And, you know, although this says it's not a problem, and it isn't a problem until it becomes a problem. And, you know, that kind of mentality is something that we have to move away from. Going forward with the proposal of the new fuels, technicians have to pay closer attention and be able to adjust with instruments. So if you don't have a set of instruments, I believe that Bruce and I have a part number for you. You can buy a set of these glasses that you see up on the screen. We'll put the part number up at the end of the presentation. You'll pay a whole lot of money for the glasses, but you won't have to use instruments to adjust your oil burners. So if you're interested, you know, just reach out, and we'll let you know how much that part number is going to cost you. So what is combustion? By definition, the rapid oxidation of two materials that will readily combine, okay, with oxygen. So what do you need? You need fuel. You need oxygen, which is obtained from the air, and you need a heat source for ignition. So you combine the three, and heat energy is released. And heat energy is what we're concerned with. There's byproducts in combustion, but byproducts are not so much our interest. We prefer not to have them, but the heat source is of tremendous interest. Carbon and hydrogen, okay, oxygen and nitrogen. You combine them to get CO2, H2O. There is a flame present that you're seeing, but this conversation is about combustion being a chemical process. And if we can get people away from thinking of combustion as being a flame that has a color or a pattern, or something that you can see by sight and adjust to a particular color or pattern, then technicians would understand that you can't adjust. You have to have instruments. BTUs, end result. That's what we're after, the heat produced. So air contains 79% nitrogen and about 21% oxygen. Our interest is really the oxygen in the air. The nitrogen has minimal reactions during the combustion process for us. There are other chemicals in that mixture, but they're very, very minute levels. And those basically are of no interest to us. And many of them just go along for the ride. And there are no byproducts from some of these added chemicals in the combustion process. So, a wicked echo. So, how we get rid of this echo? Let's see.
Bruce, how do you get rid of the echo?
By hyperthermalating in the paraplastic flaw.
Okay.
Yeah, I don't know.
Well, there it wasn't echoing.
Well,
It was only when Angel was talking.
all right. Any better? Is the echo gone, guys? Just
Gone.
nod your
Much
head
better.
so Bruce could see.
Much better.
Yeah. All right. We had some volume up. So this slide shows you the different elements and variables in the combustion process, the heat generated, number of BTUs. We typically use 140,000 BTUs available in a gallon of fuel oil. The actual number is 138,690. But that's not an easy number to calculate, so 140,000 is the standard. This is showing you at what points we're vaporizing, where the carbon burns, where the hydrogen burns. And you'll see as I go on that I use the term burns quite loosely because, again, it's a chemical process. When we think of the word burn, we think of a flame. We think of something that we can see. But burn really is a reaction that's from heat. So it's a chemical process that generates heat. Here again, flame temperatures, 2,000 to 3,000 degree. Oil can generate 140,000 BTUs per gallon, assuming an efficiency somewhere on 85%. So we're putting 119,000 BTUs into that appliance. The other 21,000 is released up the chimney. So what elements are we looking for and what are we concerned with when we talk about efficient combustion? Well, how about air? Air is the one thing that we basically control. How much air? What about excess air? Why do we call it excess air? Why does it have to be excess air? You know, the imperfect process of combustion requires that we add extra air so that we can get the oxygen content in that air for the combustion process. Draft. Do we have draft? Is it negative draft? Is it positive draft? What are the consequences of good draft, bad draft? Those are the things that we will talk about. And temperatures. What are the different temperatures? Well, we take combustion readings at steady state, static temperatures. So we can't take a combustion test when the burner first starts. We have to allow the equipment to reach its steady state operating temperature. And what about ambient temperature? What about the temperature of the air that's coming into the combustion process? Is that of importance? Well, all these things are, and they do matter, and we'll discuss it. Fuel. So our concern here is oil, atomization, and grade of fuel. Grade of fuel might mean different quantities of bio. It could also mean different types of fuel. So number 2 oil, number 4 oil, number 6 oil. All those fuels were viable at one time, and they each had different properties, and each one had different BTU content. And as we talk about, the BTU content, as we increase our bio ratio, so the caloric value of the fuel is also going to change. Something that may not be consequential to the applications that we're applying to, but there are different values in terms of BTU release from the fuel. And it's something that we have to consider going forward. Burner nozzles, so a method for atomizing the fuel and metering the amount of fuel. And, Nozzles are a pet peeve for me, if you will, because many technicians feel that a nozzle that's close is good enough. And when I speak to that, you know, the one thing that I want to ask them is, if you went to a parts store and you went to buy spark plugs for your car, and the guy says, well, listen, I don't have this exact spark plug, but I got something left over from a 1962 Volkswagen, and this is really close to what you need in your car. Is that something that you feel comfortable putting in your car? And, you know, the head shakes and the smiles, and, you know, clearly everyone understands that if it's not exact, you can't expect to get the right results. And sometimes not getting the right results can be, you know, very, you know, threatening to the operation of the equipment. So it is important that you stick to specs and understand that when you move away from specs, you're not going to get the results that you thought you would. Draft. Most people understand how to measure draft, and we know what good draft is, what bad draft is, maybe what too much draft, you know, would be. But what are the effects? And, you know, what causes the draft? And how did you make a change? How did you impact the amount of draft that you have on your particular application? Or was it caused by something outside of anything that the equipment has control over? Is there a situation with the chimney? Is there something outside that's causing poor draft? It's not always easy to understand, but it's something that you need to look at and something that you have to know has an effect. We've got natural draft. We've got power venting and induced. Anytime you have mechanical draft, from my experience, I see oftentimes where a mechanical draft device is misapplied, too small, too large, not properly installed. All these things matter. Sometimes a mechanical draft device is installed because there was an issue with draft that was not fully understood. And by not understanding that the causes of the poor draft had more to do with the layout or the equipment or the firing rate or the appliance itself, they install something that becomes unnecessary and just sometimes makes the problem a little bit more difficult to solve. Negative pressure, positive pressure. Most technicians understand negative pressure, negative draft over the fire, negative draft at the breech. You know what you got, very easy to conceptualize. But positive pressure is not always well understood. Many technicians feel that equipment operates better when it operates against negative draft and not positive draft, not fully understanding that some setups are designed for positive draft and they will fire better under positive pressure. So it is important that we explore negative and positive pressure applications, that we understand the difference and know why they exist. Measuring draft. You know, we all tell stories and hear jokes. You know, back in the day, you use a puff of smoke from your cigarette to measure the draft. And, you know, if it got drawn up the chimney, yeah, good draft. If it took too long, well, maybe that wasn't such a good draft. You need a reliable gauge. You have to have a proper gauge to measure draft, and you have to know where to measure it. You know, some of us maybe, you know, technicians better experienced than others. Some of us maybe supervisors or other roles. You walk into a situation where you see a technician measuring draft, and clearly he's measuring in the wrong place. Clearly he's measuring under the wrong conditions. Clearly he doesn't understand the functions of the chimney and what effects it has on draft. So again, things that need to be understood for proper combustion. Testing. Many guys understand how to do a combustion test. you know, they have an analyzer, they plug it in, it's digital, it gives them some kind of readings. The only thing they need to do is possibly select the fuel type, and then they expect some type of results to be, you know, given back to them from that analyzer. And they look at these numbers and they say, well, okay, my CO2 is X and my stack temperature is Y. Those are good. Or they look at these numbers and they say, well, they're not good, but have no clue and no understanding of why they're not good or what steps are necessary to make those changes or affect those changes that they need to do. So understanding the numbers is the first step for any technician doing a combustion test. Understanding how to do a proper combustion test. And everybody discusses combustion testing. We all talk about it. We all take technicians, run them through the routine. And sometimes they do understand. Often they don't. They just go through the motion. And if the numbers are good, they're happy. And sometimes even if the numbers are bad, they're still leaving their test results behind. And that part, you know, is bad. Typical printout you might see when they have their results. And this is where we start to question technicians. How did you get to this number? Is that number correct? What should your stack temperature be on that appliance? You've done these tests more than me, more than the average guy. You know what this appliance produces. If it's supposed to be 450 and you're seeing 300, why? If you're supposed to see 450 and you're seeing 580, again, why? What is happening? What are these numbers and why are they changing? The most common misconception that technicians might have when doing a combustion test is a lack of understanding of what the O2 means. They know it means oxygen. And, you know, somebody told them that and they said, well, you know, this is good. I've got 4.5%, I've got 5%, 5.5%. And the question is why? How did you end up with 5.5%? Where does that number come from? And most technicians will not be able to answer that question. These are the things that we explore when we get our results. So how much heat was produced by the combustion process? How much of that heat was absorbed by the appliance? And then we look at our unburned product. There shouldn't be any soot. Today's modern equipment operates clean, so there's no soot. Is the carbon monoxide level acceptable? There's always going to be some carbon monoxide in the results. Sometimes it might even say 0. If it says 0, it may not necessarily be 0. It may be that our instruments are not sensitive enough to see those very, very small. Although there are no consequences from a very small amount of carbon monoxide, it's still there. It's not perfect combustion, and we all need to understand that. Where did the carbon dioxide come from? You know, I'll take you back to the first slide. You know, CO2, carbon and oxygen. One comes from the fuel, the other one comes from the air, from the oxygen in the air. These are byproducts that are left over after the combustion process. So there was a chemical reaction here, and we started out with a few elements, and we end up with these compounds at the end of the process. Combustion efficiency, steady state efficiency. There's still a few people who don't understand the difference. You know, the AFUE number that's written on your boiler, that's not the combustion efficiency number that you demonstrate to your customer. That's not necessarily the number that the customer is asking you to achieve. You need to be able to explain the difference between the two, possibly even understand why these numbers don't match up. Steady state efficiency. So how many guys will leave behind a printout for the customer that shows a high efficiency, combustion efficiency number, yet when you look at the flue gas temperature, it was probably taken early on in the heat cycle, and flue gas temperature is running somewhere around 300 degrees, 310 degrees. That's probably cold water running through the appliance or cold air running through the appliance, and you haven't yet reached your steady state temperature. Thermal efficiency, heat transfer on an appliance. Important to note, you know, a single pass appliance where the heat passes the exchange, the heat exchanger one time on its way into the flue, as opposed to heat passing through the appliance several times. Here's a multi-pass boiler. That one happens to be steam. And, you know, we have a 3-pass wetback. This is more like a Scotch boiler type of setup. And it's much more efficient because we're pulling the heat or extracting the heat out of the flue gases because it has several passes over the heat exchanger. So when you do testing, what do you need to test? Yes, sir. Got a question?
Chris Murray says he flies down.
Yeah.
I'm just reading the comments as they come in.
Hey, thank you, Chris. So draft, again, we're looking at positive or negative draft. We need to understand what the appliance requires, and that's what we're looking to measure. If we're not, then we need to make the correction. Smoke. You know, here's where we get hung up sometimes in discussion, because there's still guys out there that believe that a trace of smoke is a good setup. And I could argue all day that there's no need for smoke. I don't care how efficient you want to make your appliance. Today's equipment does not operate with any level of smoke. It should never be smoking. And then you have the guy that tells me that, well, I could set it up by sight, and if I take a smoke test, I know that I'm not going to set up my boiler. Well, that's true. But then the question that you pose is zero smoke really just zero? Could it be less than zero? If there's a scale of 0 to 9 where you're indicating smoke and you're starving for combustion air, so what about that scale below 0 where now instead of starving for combustion air, you're applying too much combustion air? That's going to show up on a combustion test. It's not going to show up on a smoke test. So understand smoke. Carbon monoxide, you know, we try to get levels less than 50 parts per million, less than 100 parts per million. The code, the numbers are actually quite higher than that, and they're acceptable. But for good combustion, there's no reason we shouldn't see low ppm. How much excess air? Well, if you wanted perfect combustion, you know, if we talk about stoichiometric combustion, you know, 15.5%, you know, CO2, then you're going to have no excess air. But with the imperfect equipment that we have, there's always going to be excess air. And here's that oxygen level again, 4.0 to 5.3. And again, the eyes are spinning. Well, what do these numbers mean? Where does the oxygen come from? So now you take them back to that first slide, 21% oxygen in the air. We introduce that in the process of combustion. And whatever's left over in percentage is what was not used up in the combustion process. So if we did not use up the oxygen, then the combustion process wasn't complete, okay? And the more air that's left over, the more oxygen that's left over, the more excess air that we've added. So these two numbers, excess air and oxygen, they're totally related. I'll put up a slide later on a chart, and you see, and this is where the eyes open up, and it's like, I get it. I understand where these numbers come from and why it makes sense. Carbon dioxide, again, not measured. This is a calculation by, I'm now going to say maybe 95% of the analyzers that are out there. Most analyzers don't have a sensor that measures CO2, but there is a calculation, and based on the fuel that you select, it's going to make a calculation to your CO2 level. The oxygen level will always be true because you have an oxygen sensor in the analyzer. So no matter what fuel you selected for your analyzer, your oxygen level is always going to be what you measure. But if you change the type of fuel, you're going to see that your CO2 level changes because it's a calculation. We talk about flue gas temperature. Flue gas temperature, well, of course, varies by type of equipment. Certainly different as the appliance becomes more efficient. We'll see lower flue gas temperature, and it's not necessarily a bad thing as long as it's controlled properly. You don't want to reach the levels where you're condensing the flue gases either in the appliance or in the chimney. But if the appliance is supposed to maintain 450 degrees stack temperature, that's what you should be seeing. If you're not, then you need to find out why. As long as you understand why, it's all good. Ambient air, why do we use ambient air temperature? Why do we need ambient air temperature? Well, the ambient air temperature is added with the combustion air. So at the end of the process, you would have to subtract your ambient air temperature to fully understand what your flue temperature is, to know what your combustion temperature was in the combustion process. And again, combustion efficiency, a result of stack temperature and CO2. That's the chart that we basically use. This chart here, identifies a sweet spot for most techs. Looking at 11.5% carbon dioxide to 12.5%. And here you can see the comparison to the O2 level, the oxygen, and how it relates in percentage to excess air. So the more excess air you add, the lower your CO2 is going to be, and the lower CO2 is going to reflect in your combustion efficiency in your end results. Are we getting any questions? Beside my fly being open? Hold on, I'm going in the wrong direction, guys. Okay. So in combustion efficiency calculation, how much heat energy is released, how much is absorbed, and what is the percentage value of your oxygen or carbon dioxide? These are the numbers used to make the calculation, and these are the numbers, this is the information that the tech truly needs to understand how he got here. Not just that he got here, and not that it's good, but when it's not good, why not? What did you do wrong, or what's wrong with the appliance? Nobody likes the word soot, but if you don't get your numbers right in your calculations, then you're probably going to end up with some unburned product. Soot, carbon monoxide, and carbon dioxide. Here we go. So should that smoke be zero? Yes, but only after you properly test the appliance. If you're not testing the appliance and you're getting to zero, is it really zero, or can it be less than zero? Quantities of combustion air required for combustion. And there's a lot of misunderstanding again about where this air comes from. You know, where is your combustion air? Habit of mine is walking into a boiler room, and as soon as I walk in, I'm looking around, and where's the combustion air coming from? And if it's not there, I'm going to make a comment. But the comment I always get back is, well, it's always worked, so it must be coming from somewhere. Okay, I can accept that. It's always work. I understand it. I live it too, but it doesn't make it right. And if it's not right, there can be the day that it doesn't work. And that's what we plan for. We plan for the worst case scenario. You know, what's the day when that boiler room door is shut and it's a cold day and you run that long heat cycle and the burner runtime is longer than it's ever been? That's probably the day you're going to run out of combustion air. And you don't want your customer to find that out the wrong way, because that's on you.
It's always when something changes, Angel.
Yep. Infiltration for combustion air. So, you know, years ago, that was fine. It was reliable. Basements were open, wide open. They were not finished basements. The equipment wasn't in a closet somewhere or a small equipment room somewhere tucked away in the corner. Can't count on infiltration for combustion air. There are guidelines for combustion air openings. And how many techs actually know these guidelines? How many techs actually follow the guidelines? Confined space. Confined space can be an issue. And I've seen it happen where there is so much clutter in the basement that there is no air for combustion. These are rules that some people understand, and then there are those that ignore them. Negative pressure. Still pretty common today, you know, especially in newer construction now. Houses are getting tighter. People are removing all types of infiltration by insulating, adding new windows. You know, and if you're running exhaust fans in the house, whatever type, they all add up. You know, how many bathrooms in your house? How many exhaust fans? What do you have in that kitchen? So you got that $40,000 kitchen and you got that big exhaust fan that'll probably suck a baby right through it if you're not holding on too tight. All these things add to the negative pressure in your house. How many of us have walked into a restaurant and when you go to open the front door to walk in, you need two hands to pull and you hear that gush of air go through as soon as the door is open? That's because the cook closed the door or the window in the kitchen and they got the exhaust fan running and they've set up negative pressure in the space. You need to introduce combustion air mechanically. You could put some sort of a device. This one here looks very similarly to a fan in a can. And you're introducing combustion air into the space where the appliance is located. Ducted outside air. This is a manufacturer's termination piece. So you've got outside air being ducted directly to the burner. This is a air intake kit that's adapted to the burner, and again, ducted to the outside to bring in combustion air. Burner covers, so burner cover with a proper adapter that you can connect to pipe, PVC pipe or galvanized pipe, and bring combustion air directly to the appliance. Here's my my pitch in the Carlin cap system, the combustion air proving system, which essentially is using the cover system that you see here. But the cap system is UL and NFPA approved, designed to work with a Carlin Easy Series burner. And it's interlocked, and that's the UL and NFPA requirement, that you interlock the combustion air when it is introduced by mechanical means. So there's a connector for 3-inch PVC or galvanized pipe. There is a test damper built in. There's a switch located right here in the snorkel, and that switch is connected to the primary control, allowing you to sense a blockage in combustion air. When we talk about taking in combustion air from the outside, there are guidelines for setting up the burner for the coldest air possible. So on the coldest day in that region, when that burner is drawing the cooler air, your air saturation will be greater, your oxygen level will be greater. If it's not set to a table like this, there's a good possibility you're just going to over air the appliance, and you may have some rough starts. So it's important that we follow guidelines on minimum and maximum CO2 levels based on outside temperature. Flame retention, a concept often misunderstood by technicians. Here's something that you cannot see. No matter how many times you look inside that peephole into the combustion chamber, you can't really see whether you've got good retention on that head, on that burner. It's assumed the flame looks good, the flame has the right color, it's crispy, it's sharp, the tips are nice, it's not too orangey, it's not too white. You know, these are all the things that technicians are looking for. But do you have good flame retention? It's only one way to know. You got to take a combustion test. You got to understand what your numbers are telling you. The concept of flame retention, high pressure, low pressure, what causes the flame to pull back and burn tight against the head. How much air, how many CFM of air are you allowing as you roll that flame retention head up further in the air tube or pull it back? What happens when you open the air band on your burner? You're allowing more air, so is that greater static pressure in your air tube? Is that less static pressure? How is that affecting your flame retention? Too little air, too much air? Concepts that sometimes take time to explain and understand to the average tech. But once understood, it makes it that much easier to adjust a burner and understand why your burner may not be running correctly. Different tools for setting flame retention. Our burner uses a sliding scale on the chassis of the burner. Here we've got some tools that can also measure the setting of the head in relation to where it sits inside the air tube. Nozzle pattern. And this is an area that seems to be very confusing for a lot of technicians. Why do you select the nozzle pattern that you selected? Why is it a 45-degree semi-solid or a 70-degree hollow? What do these numbers mean, and what are you doing by changing the nozzle pattern? Well, most will tell you that they're trying to match the combustion area. So a wide area, okay, short and wide, they're thinking 70, 80-degree nozzle. A long combustion chamber, now they're thinking 45-degree nozzle. And although that sometimes is true, the nozzle pattern and spray angle has less to do with the dimensions of the combustion chamber than it does to the air pattern that exits the front of that burner. You have to match the air pattern. So you can't have the air pattern of the burner coming out at a 70-degree angle and put a 45-degree nozzle. Or you can't have a 45-degree air pattern and put a 90-degree nozzle in there. It has to be a good and not mixing the air properly with that atomized oil, then you're going to have more excess air than needed, and you're not going to have good combustion. Measuring draft. What are we measuring? What are we looking for? Well, every appliance manufacturer will tell you what they expect to see in draft over the fire. And in order to achieve the draft over the fire, this is what I need to see on the breech, on the smoke hood side of the appliance. So whatever draft I get back here determines the draft that I'm going to see here. If you're not measuring draft over the fire, you're wasting your time measuring draft at the breech, because that's telling you that your chimney is working, but it's not telling you what's happening in your combustion chamber. Should you have negative or positive? Again, whatever the manufacturer specifies for that appliance, that's what you're looking for. That's what you're looking to set up. Mechanical draft. Do you have the right mechanical draft system? And are you applying it correctly? Are you causing too much negative draft by inducing the draft by mechanical means? Did you really need to have that mechanical draft system? Or is it just a forced draft application? Are we pushing the flue gases through the appliance? Well, if we're pushing the flue gases through the appliance, you're set up for positive pressure, and your setup has to reflect whatever the specs are for that appliance. So it's, again, relative that when you walk into an application, you understand the equipment that you're working on, and you have a really good understanding of what the specs are for that appliance. You've got to make some kind of an adjustment for spec. In a negative draft appliance, the flue gases travel through the boiler quite easily. And that's what they're designed to do. So your setup, your excess air is set up minimally for a negative draft appliance. We use this slide mostly for commercial training, but in a commercial application, you'll notice there's a damper in the back, and the purpose of the damper is to restrict the flue gases as they leave the boiler. In commercial jobs, I can't tell you how many times technicians feel that opening that damper full wide open makes the burner run better and easier to adjust. And that's not necessarily the case. Forced draft boiler is designed to hold the gases tightly in the boiler. And as those gases exit the boiler a little bit slower, that means they spend more time inside the boiler, so there's better heat transfer. It also means that they're under pressure while the combustion chamber is taking place. Combustion, atomization, air mixture, oxygen. It gives us a better opportunity to create this mixture and better results in combustion. Barometric draft control. Well, this is probably the most ignored component on a system. I see them installed wrong all the time. You know, the most common mistake is the screw just drives right through, prevents the damper from opening fully or even opening at all. Sometimes it's done on purpose. Sometimes they'll put a screw through it so it doesn't open, so it doesn't blow back whenever the appliance starts. What was the cause? It's not the barometric. The barometric didn't cause the flue gases to back up. There's a different problem. That's what needs to be addressed. The barometric is there for a reason. It needs to be applied correctly. You look at a device that's installed correctly. So is it in the right location? Is it plumb? Is it vertical? Are the weights correct on the damper? Are they on the correct side? Some of them depend on whether it's horizontal or vertical. Are the weights even there? And What did you do when you added the weights or adjusted the weight and you turned it? What were you trying to achieve? Were you taking a draft test at the time? Common causes of poor draft. You know, there's quite a few. You know, cold air leaking into the chimney, flue gas temperature not high enough, too many elbows, too much pipe. If it's an outside chimney and it's not lined and your appliance is putting out very low flue gas temperatures, well, you're going to condense. You know, I've seen buckets, not necessarily on oil-fired appliances, but on gas. I've seen buckets in the basement underneath that last elbow to collect all the condensation that drips out of that elbow. Instead of dripping onto the basement floor, it drips into a bucket. Why? What causes that? Negative pressure boiler room. Again, more common than we sometimes understand. Technicians should be instructed that when they walk into a boiler room or a furnace room, and more important, a furnace room probably, close the door behind you. When you walk in, you're going to do a test. Close the door behind you. When that fan comes on in the unit, is it drawing air from the room? Do you have that many leaks in your ductwork that you're creating negative pressure in the room? Heat exchanger clogged. Common thing for technicians to do. The heat exchanger's clogged. What do? I don't want to clean this. Hey, put a smaller nozzle in there. Small nozzle takes away the back pressure and they move on. Let the next guy worry about it. It was, huh? Yeah, this picture here comes off of a gas burner installation. They've got the spill switch on there, but that's the wrong screw. That damper's never going to open. It's the wrong barometric. It's an RC barometric. There's no weight on it. You know, there is no safety here on this barometric, and that is more typical in what we sometimes see out there than not. So you got to use test instruments. Nobody can set up the burner correctly unless you got a pair of those glasses or you're using some test instruments. What are you looking at when you look at the fire? Okay, there's nothing to see there. I challenge technicians to adjust a burner without ever opening that PEEP door. When you're done, go ahead and take your smoke test, open the PEEP door, and take a quick look and see if everything looks fine. Guaranteed that if you got good results, it's going to look good when you look at that PEEP door. All right, so some of the numbers that you might want to be looking for when you're doing your combustion tests. These are the numbers that the manufacturers would specify when you're doing setup and testing. These are decent numbers. Are you getting these decent numbers? And if you're not, then you need to understand why not. Isn't it? All right, guys, so right on time. I'm surprised. Are there any questions? Anybody have something you want to ask? Myself or Bruce? All right, don't everybody jump in at one time. Well, I appreciate you guys taking the time. I thank you, everybody. Have a good night. Stay safe. Hope, well, if you're still on, I guess you still have power, but I hope everybody has no issues for the rest of the evening. Thank you. Good night.
Thanks, Angel.
You asked the question.
Who are you unmuting?
I can. Hey, hey, Angel. Can you hear me?
I can hear you now.
No,
I can't hear a thing.
You know what?
I'm not muted.
I won't talk, but I'll listen.
Can you hear me?
Hang on, he's gonna turn up the computer.
Is that red? I don't know how to turn my camera on.
On? We've been watching you. We've been watching you.
No, I think I'm unmuted.
No, yeah, you are. You're unmuted. We've been watching you eat corn chips and stuff and cheer for the Mets. How'd they do?
Oh, you were listening to me.
No, we couldn't hear you, but we could. We were watching the movements.
Oh.
What's that?
She had a presentation.
Oh. Your broadcast engineer is sleeping.
Yeah.
There's no bar here, Carlin, which is sterile. Maybe you should get sex out. You're going our own. I know.
Okay, so we're done, Angel?
I'm gonna end it.
Stop the music. See you, everybody.
Good night, everybody.